Hi, welcome to video 8.5a part 1, partial fraction.
Using partial fractions, but we're going to start with just understanding what that means. So it's the process of breaking up a single fraction into the sum and or difference of two or more fractions. So, for example, the first set of exercises they're going to give you, there's no integration at all. It's just write the form of the partial fraction decomposition of the rational expression. Do not solve for the constants. So, you'll notice in each case we're given a single fraction. And basically what you're asked to do is rewrite it as the sum and or difference of two or more fractions. Now, basically what we're doing is we're doing the reverse operation. You're used to adding two fractions. You find the common denominator by looking at each of the factors in the denominator and taking each of them to its highest exponents, the LCD, lowest common denominator, lowest common multiple of the denominators. But what we're going to do is we're going to work backwards. So we're going to say, oh, if we have a single fraction whose denominator is the product of the factors x plus 1 and x minus 2, it must have come from a sum or difference of two fractions, one with a denominator of x plus 1 and the other with a denominator of x minus 2. So same idea right here, and I'm going to go actually in this direction because this is what we'll be doing. So if you have a single fraction with a denominator of x squared times x minus 5, obviously we need a fraction with an x minus 5. Now you might think we only need a second fraction with x squared, but you have to think of all the different possibilities. And one of those possibilities is that there might also be a fraction with a denominator of x, because that would still give you an LCD of x squared times x minus 5. So basically, if you have a factor to an exponent, you're going to have that as one of your denominators, and then you're also going to have the one with the lesser exponent. So for example, if this was x cubed, you'd need a fraction with an x cubed denominator, another fraction with an x squared denominator, and another fraction with an x denominator. And similarly, so this is just giving you an example. If your single fraction denominator is 8, that could just as well be a fraction with a denominator 2 plus so many quarters plus so many eighths. You can't just assume it has to be all eighths. Okay, so for example here, my denominator for my single fraction is x minus 1 cubed and x times x minus plus 5, squared. So we could have an x minus 1 cubed. We could also have an x minus 1 squared. We could also have an x minus 1. As far as this one goes, we could have an x plus 5 squared. We could have an x plus 5. So that would be actually 5 different fractions. I promise you it won't be that bad. Okay, so here's an example. Write the partial fraction decomposition for 1 over x squared minus 5x plus 6. The first thing you're going to do is factor the denominator. So when you factor the denominator, you get x minus 3 times x minus 2. So then you say, okay, so I've got this fraction, 1 over x squared minus 5x plus 6. I know it's equal to the sum of two fractions, one with the denominator of x minus 3, the other with the denominator of x minus 2. I don't know what their numerators are. They are constants, because this numerator is a constant. But, and even if it wasn't, it won't matter. I'll just call them A and B. Now, do keep in mind when you get my solution key back from a test, I might have put my x minus 3 here and my x minus 2 here. My A might be your B, my B might be your A, but it doesn't matter. Okay, now I'm going to put plus. If it turns out that it's actually a difference of two fractions, the B will be negative. So just assume it's plus for now. So I have an equation, and what I'm going to do is multiply both sides of that equation by the LCD of both sides, which is, of course, since this one is x minus 3 times x minus 2, is x minus 3 times x minus 2. So I'm going to multiply both sides by that. So on the left side, of course, they just cancel out, and I'm left with 1. On the right side, when I multiply this expression by the first fraction, the x minus 3's will cancel, but I'll be left with a times x minus 2, which is right here. When I take this expression and multiply it by the second term, the x minus 2's will cancel, leaving me with b times x minus 3. Okay? Now at this point you might say, well, I'm no further ahead. Now I have 3 variables. But basically, this is what they call the basic equation. This is always going to be true for any value of x. So I very carefully select convenient values of x. If I replaced x by, say, 7, I'd still have an equation in two variables, a and b. But if I get clever and I replace x by 2, this whole a term will disappear, and replacing x by 2 will give me negative b. I can solve for b. Similarly, if I replace x by 3, this whole term will disappear. Replacing x by 3, I'll be able to solve for a. So, because this equation is to be true for all x, you can substitute any convenient values for x to obtain equations in a and b. The most convenient values are the ones that make particular factors equal to 0. So, the first thing I'll do is I'll let x equal 3. That'll give me, on the left side, I still have 1. I have a times 3 minus 2 plus b times 3 minus 3. That'll give me a equals 1. Now I have a. I can do the same thing to find b. I'll let the factor of attached to a, I'll let that go to 0 by letting x equal 2. So when I do that, left side and right side, I replace the x's by 2. This whole thing disappears, and I'm left with b equals negative 1. And we have now taken our fraction, which was this original fraction. Remember, we said it was a over x minus 3 plus b over x minus 2. Well, a is 1 and b is negative 1, so it's plus negative 1. So it's really not a very difficult process. You might have seen it before in pre-calc, probably not. All right, so here's another example. If the original denominator was x minus 5 cubed, you'd need one fraction with an x minus 5 cubed, one fraction with an x minus 5 squared, and one fraction with an x minus 5. So I'll call those numerators a, b, c. You're then going to take this equation, multiply both sides by the LCD, which is x minus 5 cubed. On the left, you'll be left with 4x squared plus 3. On the right, the first time you multiply, the denominator will cancel completely, leaving you with just a. The next time, you'll multiply through, x minus 5 squared will cancel with 2 of these, leaving you with one of them, so you'll have b times x minus 5. And in the last case, one of them will cancel, leaving you with c times x minus 5 squared. So, not too hard to figure out that you're going to let x equals 5. So that number does work very nicely because it makes both of these factors go to 0, and I get a equals 103. The problem is there is no other number to let x equals, and I still need to find two variables, b and c. So remember, this is true for all x. So literally, pick anything you want, okay? So far we've used 5. Pick nice convenient numbers like 0. So if I take this expression on the left, if I replace x by 0, I'll get 3. Then I'll get a minus 5b plus 25c. Okay? Then, now again, I can't solve this because it has two variables. But if I let x equal some third different number, like 1, again, plugging 1 into here on both sides, you'll get this expression. Well, that is now a system of equations, and you can solve that system of equations. Okay? So that's going to be, I just sent it to the other side, 5b minus 25c equals 100, and negative 4b plus 16c equals negative 96, and etc., etc., etc.